Hello, my name is Robert Nemeth, and I will be presenting the paper Targeted Attacks on Teleoperated Surgical Robots, Dynamic Model-Based Detection and Mitigation. Before we begin, I would just like to acknowledge the researchers behind this paper. They were all from the University of Illinois. Some were at the Coordinated Science Laboratory, and others were at the Healthcare Engineering Systems Center. This paper was presented at the 2016 IEEE IFIP International Conference on Dependable Systems and Networks, and the link to the paper is below. As a general overview to the purpose of this paper, it notes the increase in use of teleoperated surgical robots, and as their usage increases, it becomes important to identify any potential attacks. Now, attacks on these robots can create several issues. It can cause damage to the robot. There could be unavailability of the system during surgery. It could also have unexpected robot behavior where motions will be jerky or cause patient harm. And realistically, all of these can cause patient harm, either through physical tearing and perforations or through just the inability to actually perform the needed surgery. The researchers counted potential attacks through a model-based analysis framework. And this framework will estimate control commands, such as the motor positions and the joint positions, and this prevents potentially harmful actions if they're outside of safety thresholds. On average, there was a 90% success rate. There have been several previous attack studies for teleoperated surgical robots, but the primary focus was on disrupting communications between the console and the robot itself. This was done through denial of service attacks, where the communication packets would simply not reach the robot, as well as man-in-the-middle attacks, where the communications were altered to be harmful before being sent to the robot. This was the first study to examine the possibility of direct compromise of the control systems. This did assume the ability to install malware directly to the system, either as a system user or through remote code execution. Compromise of hospital security systems has been examined in depth, and we will touch on that briefly later. Teleoperated surgical robots are robots that are used for minimally invasive surgical procedures. They provide better visualization, such as a 3D magnified view of the surgical area, and since these are invasive, it's actually a 3D view of the inside of the patient. It also offers increased precision with the teleoperated arms and instruments, and since these are inside the patient, it allows for minute movements that would be more difficult to do by hand. Between 2007 and 2013, there were 1.74 million procedures done robotically in the United States, and they plan for future robots to be able to operate in extreme environments, such as battlefields, underwater, or even space. There are several components that are common among surgical robots. These include the console, where the surgeon can actually view what is being operated on, the robot control system, which controls the manipulators and the arms, and the patient side cart that has extra instruments and other pieces of surgical equipment. The key component is the electronic control system. This is responsible for all of the commands and safety checks. It receives commands, translates commands, provides video feedback, and performs the safety checks. The robot pictured here is the Raven 2, which is what was actually used for this experiment. Now, the Raven 2 is an open source surgical robot. The commands are sent via Interoperable Teleoperation Protocol, which is known as ITP. This is based on UDP, so the packets do not have a secure handshake receipt. For this experiment, the Raven 2 was treated as a gray box, meaning the researchers acted as if they did not have access to the source code. Physically, the Raven 2 systems have two cable-driven surgical manipulators, with DC motors and 7 degrees of movement freedom. On the software side, it's a node process on the robotic operating system Indigo, which is the common robotic operating system. It also runs on a real-time Linux kernel. This one used Ubuntu 14.04. The image shows the general control structure of the Raven 2. The physical side is on the left, where you can see the human operator is interacting with the console, sending software changes to the control systems, that impact the actual physical robot. The right side is all of the software side, which we will cover a little bit more later. In regards to the Raven 2's cyber-physical design, we have a programmable logic controller, and we also have two custom 8-channel USB interfaces for actually sending the messages. There's a PID, which stands for Proportional Internal Derivation Controller. This calculates the amount of torque that was entered by the operator, as well as promotes safety checks within to make sure that everything is within a specific threshold. All of this happens within 4 phases for the Raven 2. There's the emergency stop, or e-stop, which happens when the machine is off, or when everything has all the power cut to it. There's also initialization, and this is after the machine is turned on and safety checks are performed. Next is the pedal up state. Now in this state, all the safety checks have passed, and the robot is ready to be initiated by the operator. There is a physical foot pedal that the operator will push, and when it's down, the robot is in pedal down state, meaning that it will actually accept input commands and move to where it is being requested. In terms of safety mechanisms, the first one is the physical start button. The machine will not operate unless the start button has been pressed. There is also those foot pedals. They disengage the brakes when depressed, and they also engage arm movements from console. If it is not depressed, none of those will happen. In software, there are threshold checks performed by the PID, and there's also a watchdog signal that is sent to the PLC through the USB. If that signal is not available, the emergency stop is automatically triggered. The researchers looked at 2 primary attack types for the Raven 2, both with similar outcomes. There is unintended input injection and unintended motor torque commands. Both of these attacks would cause the robot to move in an unexpected way. It was implemented with Bash, Python scripts, and general ROS commands, and the execution only required user access. It did not require root. Now there were 3 main phases for this attack process, each of which will be discussed in detail. There was the preparation phase, the analysis phase, and the deployment phase. During preparation, the goal was to eavesdrop and intercept USB communication, and then log these packets. After logging, they would forward these to a remote server for future analysis. Most programs do not directly call the kernel in Linux. They instead invoke a function that then accesses that system call. With user privilege, an LD_preload environment variable can be created. Once this variable is made, all future terminals started by this user will have that environment variable set up, and then it can point to the malicious shared library. In the library, a malicious function with the same exact name as a general system function is created. In the example picture, they used the write function. The wrapper code will run its own code, and then at the end call the original write function, so the system doesn't even know that it has been compromised. After all the packets have been received, the next phase is to analyze them and look for the state information based off of different patterns. The Raven has 4 states, and this is known through the public documentation. The analysis was done over several runs and different logs, and because the format was unknown, they had to analyze every specific byte to try and find these patterns. In the image on the right, it shows the packets of byte 0, which is the packet that was actually used to determine the state values. The researchers determined that byte 0 switched between 8 values, whereas the other bytes would toggle between many, many more. The 5th bit would toggle between 0 and 1 periodically, and because it was periodic and consistent, they determined that this was likely the watchdog signal. The 4 remaining values would correspond to the 4 states of the Raven 2, and these are pictured on the right on figure C. You can see it starts in E-stop, then goes to homing, which is the initialization phase, the pedal up, and pedal down. Now that the states are known, the attack can be carried out. The goal is to install code that will trigger an attack while the robot is engaged in a surgical operation. The write call is modified so that in addition to sending packets, it will also check the state, and if it's in pedal down, it will modify the values of other bytes in that packet. The control system performs safety checks, but it does not perform integrity checks. The attack takes advantage of this fact by modifying the values after that first safety check has passed. After implementing this attack, the researchers wanted to evaluate what would happen to the physical systems if this did occur. They tested it on both a surgical simulator and on a physical robot. This gave them the advantage of not needing to worry about damaging a simulated robot, as well as not worrying about damaging an actual patient. In regards to the physical system, there were many consequences. There were abrupt control arm jumps, there were several e-stop triggers, and there was even simulated cable breakage. Because the malware is installed to the LD preload variable, this is triggered every time the system loads, so even if it's restarted, it will just occur again. Now, past FDA studies have reported several injuries from unexpected movements of these robots. With these attacks, it makes it very difficult to distinguish operator error from malicious injections. In the software realm, the performance was measured by the execution time of the wrappers. There were 50,000 runs, and on average there were less than 30 microseconds of overhead. The Raven 2 has a timing constraint loop of 1 millisecond, meaning that all actions have to occur within that moment. Because it's 30 microseconds, there is no adverse performance on impact or on control that were not malicious. The effects are completely unnoticeable by the operator. On the right is a table that shows the averages for the performance overhead of the different system calls. The baseline call took the least amount of time at about 1.3 microseconds. The injection took about 3.6 microseconds, and the logging took the longest at about 20 microseconds. There are several reasons that this attack would be extremely difficult to detect. First, it's limited to the robotic control software itself. There are no separate processes, there are no system-wide activities within the Linux kernel, and performance is unaffected unless it was the malicious call. It has the exact same control flow, the commands are routed in the exact same way. It has the same command syntax, everything happens exactly as it did. And because there's that 1 millisecond control flow for the Raven 2, most detection would cause overhead that would go beyond that 1 millisecond. And even then, the attack could still be missed. To combat the attacks, the researchers created a dynamic model-based framework. This framework serves two goals. First, it can assess the impact of attacks on a physical system, just by simulating it. And then it can also create preemptive detection of these attacks. It was validated against the same two attack techniques that were discussed earlier, unintended input injection and unintended torque commands. One of the primary challenges is in regards to the estimation techniques. The system will need to check the input commands as well as the output commands and verify that they follow a logical flow against other previous commands. There are also the tight time constraints, the 1 millisecond loop of the Raven 2 robot. Pictured here are the general components for the framework. First, we have the console emulator, and this mimics the teleoperation console. It'll send and generate user packets based on previously collected surgical movements and trajectories. There's also a graphics simulator. This animates the robot movements in real time, and they were generated using 3D CAD models. There's also a dynamic Raven 2 model, and this is actually a simulation of the Raven 2's physical system. So it integrates the motor dynamics, the robot manipulator dynamics, and it simulates it in real time. Lastly, we have the attack injection engine. This allows them to create multitudes of different attack possibilities with different values at different timings, and simulate as many attacks as possible. To ease the use of testing this dynamic model, it models the motors that are used by the robot and manipulators, and it can run with or without the physical robot. It receives commands, and it estimates the next motor and joint positions. The primary challenge of this was time. To keep down the CPU cost, they only modeled the first 3 of 7 degrees of freedom. There were 2 rotational joints and 1 translational joint, similar to your shoulder, elbow, and then a tool insertion or retraction mechanism. The researchers chose these joints because they contributed primarily to the end position, whereas the next 4 primarily affected the orientation at the end of the movement. Mathematically, the researchers worked with 2 different types of second-order differential equations. They worked with both a Runge-Kutta solver as well as an Euler solver, using the ODINT numerical package in C++. The model would measure the physical properties of the robot, such as inertia and mass, and the coefficients were obtained by manually tuning the physical robot itself. They validated their estimations against the actual movements. After 10 runs, they determined that the Euler method was faster, averaging 0.01 milliseconds as opposed to the Runge-Kutta's 0.032 milliseconds. On the right are charts that demonstrate the average estimation as well as the actual movement values, as well as the average error between both mathematical methods. With the framework integrated, the researchers did an attack impact assessment without any prevention of the attack. They attempted with thousands of injections, and they noted that small malicious torque commands did not have much impact if they were less than 64 milliseconds in length. This is because the PID controller will actually correct the motor velocity errors within that 1 millisecond control loop, and if it's a small value or a small period of time, it just does not affect it. Unfortunately, if the PID is in place, the abrupt jumps are not detected by the Raven. The PID will only check commands against a fixed threshold. They don't actually take into account the impact on the state of the robot. And since the safety checks are the last stop before sending, and there's no integrity check, it allows for a gap in systems targeting. The next step was to integrate the framework into the system and actually build up an anomaly model. Based upon feedback from surgeons, the idea was to detect unsafe jumps of more than 1 millimeter within 1 to 2 milliseconds. The detection mechanism will intercept DAC commands and then estimate the next motor velocity in joint motor positions. These thresholds of acceptable values were built over 600 runs, and then they took the 99.8 and 99.9th percentile of the thresholds and applied that to any future movements. 3 specific variables were looked at in order to identify anomalies. These are motor acceleration, motor velocity, and joint velocity. The graphs on this slide show the detection probabilities for both the simulated system and the actual Raven system. The probability of detecting an attack increased as time went on, and increased as the injected error values went up, but the simulation did better overall than the Raven 2 system. On average, the model would detect simulated attacks 90% of the time. The Raven 2 had about an 86% detection rate. Between both systems, torque commands were more consistently detected than user input, and the Raven 2 actually detected 13 cases that were missed by the model. After detection, there are several requirements for mitigation. First, you need to look at the corrections. The system can either force a previously safe state, or it can completely stop the command and enter the e-stop mode for the robot. The ideal position to detect an attack is just before execution. This avoids the time of check, time of use vulnerability, which is especially important due to the lack of integrity checks. We also need to take into account the potential for high computation costs. The researchers' main idea to get around this was to use trusted hardware modules that were assigned in parallel with the robot. The assumption for this attack is based on the ability to compromise the hospital network. Listed below are several attacks that have occurred previously. There was a blood gas analyzer that was exploited, and this established a backdoor to the entire hospital network. Millions of patient records were stolen. There have also been firewall breaches caused simply by scanning the network for vulnerabilities, and they've stolen employee credentials and then accessed workstations physically. In conclusion, due to the increase in the number of robotic surgeries, the security is becoming more and more important. These attacks can damage the robot, or more seriously, cause physical harm to the patient. The framework created by the researchers successfully mitigated 90% of attacks, and in combination with the Raven 2 would prevent many more. While surgical robots were the primary area of study for this paper, it is important to take these techniques into account when examining other areas, particularly when patient safety is a primary concern. This final slide are the sources for all the images and other papers mentioned in this presentation. Thank you for your time.